Thank you very much, Danny. That's a very warm introduction. I appreciate it. And it's just such a jam-packed room. So I hope I make it worth your while for coming. Thank you. So I will talk about the fundamental challenges in robotics. I put embedded AI on there to see if that might draw a few more people. So introduction. So what is robotics? Well, I tried to make a phrase for it. It involves the design, programming, and analysis of movable machines that accomplish some kind of useful work through sensing and manipulation of the surrounding world. Dan Kodachek wrote a nice paper musing or wondering about the foundations of robotics, and he called it programmable work. This picture that I borrowed from somewhere is very humanoid heavy, so I asked AI for help, and it gave some picture like this, which has more pictures of like drones and things. But if you look at it carefully, it has weird stuff like fast care, which is like some kind of weird mutation between healthcare and farming, maybe. I don't know. Here's a low sticks, looks like a logistics toaster truck. I don't know. Anyway, but this is the results you get, right? And that kind of leads into my talk in a little bit of looks fine from a distance, but when you zoom in closely, it can get weird. So robotics suffers and benefits from always being someone else's application field, I'll say. So is it applied computer science, applied mechanical engineering, applied nonlinear systems of control, applied math of all kinds? People call it interdisciplinary, but that's just another word in academia for homeless. Right? So everyone loves everyone loves interdisciplinary initiatives and all these kind of virtual centers and stuff, but that's kind of what. So it's its own field with core questions, problems, and ambitions. It's exciting, so I can see why a lot of people are attracted to it, and they've contributed many great things, some of which I'll mention. I also thought it's kind of funny. Maybe computer science is just an application of physics and logic, right? So just an application field. But at some point, it grew into a field by pushing very hard and a great intellectual development over, let's say, about a century, right? Or almost a century. Then there's AI. Is there anything that's not AI anymore, according to the popular press? I'm not really sure. I think this trend looks very much like old European imperialism to me. It's sort of like we're coming, we're gonna come to your community, we take things over, we're going to enlighten you and give you intellectual depth and make you sophisticated. We have a new religion to bring and all of this extra stuff, you know. So you're gonna do things our way, and we'll rename everything in the process. A lot of what seems to be going on. Oh, now my slides don't work. See, it's frozen now, so it's turned here, but not there.
So you have to be careful when you talk about AI.
Yes. Or maybe this picture. I don't know that it looks a bit. Yeah, I don't know what to do. So it's different on mine. So.
We can switch the presenter to computer and connect it directly.
My Wi-Fi off. Wi-Fi is still connected. I think. Oh, Danny, what time do I stop talking?
Including questions at 10 past noon.
Okay, so I'll try to stop about noon.
Yeah, people go to eat something.
I was so excited. I prepared about a 3-hour lecture. So buckle your seat belts. I'll go really fast. That looks good. Yeah, I guess what have I witnessed during my career? If I divide it into decades, I remember back in the 90s, we desperately needed data. Like, oh, I got a few images on a floppy disk, you know, digital images. That's great. Then all of a sudden I kept hearing about in the 2000s, we have big data, what are we going to do? The internet's filled with big data. And then came the perfect union in the 2010s. Big neural nets digest big data. Everybody's kind of happy for a while. And then in the 2020s and on, well, who knows what happens onward, we hear that neural nets will solve everything. So I don't know if I don't buy into that, but that's kind of what we're hearing. I've also noticed that over time. Wow. Okay. Over time, there's a gradual tendency from what I would call diverse thinking to homogeneous thinking. I noticed this well before ChatGPT. If I asked 100 students to come up with class project ideas, I would get maybe 50 different distinct ideas. And if 10 years later, it was like I get 3 or 4 ideas. And if I did a Google search on my phone, I would find the same kind of ideas coming in. So there's a lot of scary stuff like that happening. Maybe not everywhere, maybe not at Tel Aviv University. So what's different about robotics? Well, robotics doesn't just come equipped with big data. There's not all of the robot information just littered all over the internet. So but there was with images and language. Okay, so it's not the same kind of thing. The physical world also contains a lot of known symmetries and structure and laws. like gravity and Lie group symmetries and things like that. There's also simulators that people are using to generate hallucinated data because you have to feed the big data monster whatever it needs. So you use simulators to generate a lot of that. And then there's the sim to real problem. It's a bit weird to do that, like generate simulated data because it needs data, because it's a black box and it needs that. And generally, we have good models that we've developed over many decades in engineering and robotics and many other fields. But one thing that is a problem is I'll call it archaic modularity, breaking the big problem into certain sub-problems. Everybody goes their separate ways and works on it. It's useful sometimes, but it's damaging over the course of decades, I would say, as people get too stuck with certain paradigms. This end-to-end kind of learning has shown the benefits of that, actually. So Ken Goldberg likes to say, GOFI, good old-fashioned engineering will remain, but how to integrate that into how to integrate it with machine learning and how to even adapt machine learning itself is a question. So I come from motion planning background, as Danny said. It's like having models of pianos and moving those around. I'll go very fast on this. Where do the models come from? Well, nowadays you can use SLAM. I want to go very fast. I want to get to the main kind of gist of my talk. There's configuration spaces that we all like to think in. That's the space that corresponds directly to the degrees of freedom that we have. It's a space of transformations. For example, a robot rolling around on the floor makes a three-dimensional space. You have X, Y, theta that parameterize it. You have 6 degrees of freedom for a flying drone. You have robot manipulators. Each joint of the manipulator is another degree of freedom, so that adds a component to your space. And you can have humanoids with, say, 80 dimensions. And you can have a bunch of robots moving around, and you just take a Cartesian product of all of their spaces. And that's where you get some kind of configuration space or state space, as I'll say. Then there's combinatorial motion planning, which one of my favorite works is by Schwartz and Schurier. Mikhail Schurier couldn't make it today, but I was sad to be a little bit, but I wanted to meet him. Because I really love this computational real algebraic geometry stuff. When I saw that, I fell in love. I implemented it for a class project in Seth Hutchinson's robotics class in 1991, along with a friend. And we got it to cylindrically decompose S4, the sphere, and R5. So it worked pretty well. I got all the cells and everything. So it was very, and I was convinced that there was no limit to the amount of mathematics that could show up in robotics. And I just, Jean-Claude Letton's book at the time with the popular book, and it had on motion planning, and it had some beginnings of topology and differential geometry in there, and so lots of good stuff. So, oh no,
Again?
I'm frozen again. Yep. You know the procedure, I guess. Okay, that's it. That was the key. Rocking the word. So then came along sampling-based planning, because these combinatorial kind of methods were very hard to implement and not able to kind of solve efficiently industrial grade problems. So they're very interesting in theory. Sampling-based used collision detection, which is also relying on computational geometry methods in another way. And then they're just probing the space and then doing some kind of search. There was a lot of methods on those. This is pre-RRTs. Danny already mentioned RRTs. That's kind of the thing that I'm mostly sort of known for in academia. It's very, very simple. It's just a few lines of code, and it grows these kind of space-filling structures that have a kind of natural Voronoi bias to them without representing Voronoi diagram. Newton have been used all over the place. One of the latest implementations of this has them running from Lydia Kavraki's group, and along with their students, has it running in on the order of microseconds time on benchmark problems and stuff using this thing called RRT Connect. And there's a version of it for dealing with differential constraints and dynamics. And we won this milestone award thing, as Danny said, for like it was like out of 2,000 papers in that time period or something. It was the most impactful paper 20 years later. At the time, by the way, it was barely accepted and rejected from other places, but that's how it works in academia. Anyway, I got back into RRTs with my son Alex and a postdoctoral researcher, Bashak Sakchak, who's a professor now at Maastricht University. And we made RRTs about 1,000 times faster for the kinodynamic planning versions, published that recently. That's not the main stuff I want to talk about. When I think about all this stuff is like at one extreme. It's like trying to make a digital twin of the robot's environment and the robot, and putting all of that in the robot's brain, and then making everything move together in lockstep. But what I think, so there's something kind of wrong about that in a lot of ways. It's useful, and it's fine if it's useful. That's great. But what's a little more beautiful is if we can think about going towards the direction of minimalism, rather than building something like a Cartesian theater inside of the robot's head. What can we do? So there's a lot of different things that have influenced me, either things I agree with or don't agree with. I love these old like maze exploration automaton, whether using an automaton or exploring graphs. with pebbles and compasses and stuff like that. Sensor-based vehicles, which have no memory, they can do a lot of interesting things. I like an activist philosophy quite a bit. So, which is studies much more, let's say, correlations between internal states of a biological organism or an engineered sort of device, correlations between that and the outside world, and not so much obsession about semantics and meaning and all these kind of things, which I really like. I don't believe that robots believe. I don't like the word belief state for robots and things like that. And these kind of things are very inactive. So, and activism also sounds very close to what Embodied AI is trying to do. But again, at the end of the day, when I get through all this stuff, I'm much more inactive and less oriented towards semantic and symbolic things, trying to push for minimalist, and I'm kind of modularity ambivalent. I don't think we should get too stuck in particular modularity. I love Rodney Brooks's Intelligence Without Representation, not the subsumption architecture and all the stuff that came along with that, but a lot of the philosophy in there, which was trying to kind of blow up what all the big brain roboticists were doing prior to that. So let's think about something very, very important for the core here. So learning some kind of structure. So imagine we have a one-dimensional robot, and it's like moving on a track. So it's just kind of going back and forth like this. And it takes discrete steps. And there's two actions, forward or backwards, F or B. And then this is where it looks kind of, let's say, Turing machine inspired. This environment goes on forever. And we're like gods looking down on it. We can see the structure, but the robot can't see all of this. It just has a sequence of actions that gets applied, and we can have a different possible sequences. I'm trying to make this look very much like theory of computation. So instead of sigma 0, 1, I have U being B and F, and then I have the clean closure is U star there, and it just gives me all possible strings, including the empty strings. So these are all the things. So imagine we do some experiments, and each one of these strings puts the robot on some unique trajectory. And now there's a special place of interest in the environment. It's at location 2. And I have a sensor that just tells me whether or not, it tells the robot, in fact, not us anything, but we're gods, we can see it all. But it tells the robot whether or not it's at the interesting place. So if it's at the interesting place or special place, it fires a 1. And if it's somewhere else, it fires a 0, meaning boring. All right? So now I do this experiment over and over again. I put the robot back to its start. I'm going to do a learning experiment. And I'm just going to try every one of my strings, and I'm going to see what strings cause the firing to happen, right? And I'll do this for, I don't know, all strings, let's say. So I'm making an infinite data set. It's a lot of data, right? More than all the internet, so that's pretty good. Infinite's pretty big. And then after all that, I have a lookup table. If I could do it forever, I would have a lookup table where I could just say, okay, each string, I know what the output's going to be. So I've learned my world, right? I know where the special place is, what's going to happen there. So of course the table's too big, infinite's kind of big. Can we use deep learning to compress that? In fact, if you try to use deep learning on this, it's kind of weird. Right away when you use PyTorch and stuff, it doesn't like variable length inputs in your data and such. So it suggests padding and other stuff. One of my students was trying it before I came here, and he even asked ChatGPT what to do, and it started talking him into doing different problems. Well, you probably don't want to do that one. Do this, you know. But back to that homogeneity thing again of thinking. So what should you do? Well, here's one way to kind of compress it down, which we should know as gods, where we're very smart, presumably. We take each one of the strings and map it to some kind of internal information state, where it's just the number of F's minus the number of B's. So number of forwards minus the number of reverses. So if I do that, that starts forcing these strings into equivalence classes. Let's think of what strings have the same output, right? So we get these equivalence classes. So you've partitioned the set of all strings. Doesn't it sound familiar? My hill and the road equivalence classes, DFA minimization, NFA minimization could be in there as well. So all this kind of stuff is very, very closely related. It's not equivalent at some level, but very close to the foundations of computation. But I'm asking still a different kind of question. So we could start with two different partitions. Sorry, a partition into two different classes by just 0 or 1 based on what the sensor does. And we have another partition, which is the finest you can possibly have, which is saying these two strings are equivalent if and only if they're identical. And then there's just one kind of in the middle that we've just constructed. Well, it turns out the one in the middle ends up being just right because it's sufficient in some sense. So this just denotes concatenation. So I could be moving along here from step to step of the robot, just concatenating strings. And that would be fine. And that would kind of build up the entries in my table or let me query the table. We imagine it goes on forever, but every string is finite length, right? So I can query in my infinite table like this. So that means concatenation. What I'd like to do is live down here and have some kind of internal state with some internal transition function so that every time I take a step, it just does some update. And of course, what you're going to do is when you go forward, you add one, and when you go reverse, you subtract one. So that makes a very sensible thing to do. I tried to make a ridiculously simple example so that we're all smart gods looking at it and we know what to do. But I want to generalize it, of course. So that makes it go from these, makes it jump around through these nice equivalence classes over U, and it has some very nice kind of property of sufficiency, which is that I can live completely down here. I don't have to, I can go from here, and let's see here, I can go down here and then I can stay down here all the time. I don't have to go over here or back up here and come around and back down. So this makes a nice commutative diagram. So this is a basic requirement of sufficiency, but it's also the basic conditions that you want when you do DFA minimization. All right. So of course, basically this thing's calculating integer coordinates. We keep in mind this perspective. It's cute to interpret it in terms of algebra. So take the group Z, the additive group Z, the integers, and you can think about, first of all, just looking at all strings of F's and B's, and you have this relation that BF is equal to the empty string and FB is equal to the empty string. Well, that's just encoding an inverse. So that would move a free monoid to a free group with one generator, right? F. So for example, so that's cute. This is what I was saying. All that learning would have just learned one relation. So you've heard the story, a picture is worth 1,000 words. A relation is worth an infinite amount of data, right? So that's kind of the idea. You can do it in 2D. We're trying to generalize up. So I have 4 directions I can move. I make strings out of that. And then I get Z cross Z as coordinates for that. So it's just your IJ coordinates as you move around. And look, another relation is needed now. It's not a free group anymore. It's this relation that says that going this way and going this way, RF and FR are the same. That all of a sudden makes that wonderfully compact representation. Now, when you throw obstacles in there, it gets messed up, and people who like algebra don't like it so much because you lost closure, right? Everyone likes closure in your operators and stuff. You can make it kind of work anyway. You just have to define what would happen if you apply F and you're already facing that way. So what do you do? Maybe it just doesn't move or whatever. You can make some kind of constructions out of it, but it's more complicated. Is there still a minimal internal information state? I didn't say that, but those coordinates are the coordinates we're calculating are not only sufficient, but they're minimal in some way. It's the best partition of the set of strings we can get, just like minimizing DFAs. So we can make it a little more realistic by not staying on a grid. Maybe we have a car that drives around. Maybe the car drives around on a bumpy floor, so it has all kinds of things that can come in, including unpredictabilities, and you end up with a more giant mess. So I'm going to now get into the kind of more general theory, the kind of core of the stuff, but it's still from a very high level. I'm trying to leave you with an impression that there's something maybe worth reading in these papers, I hope, but I just want to give you the high level. So it's mainly works that's done in our, I like to sometimes jokingly call it our Arctic think tank. So we're way up at 2 degrees below the Arctic Circle, and it's cold and there's not a lot to do there, but we sit around thinking about mathematical puzzles and things. So Bashak is a control theorist. Kale is a mathematician who works on dynamical systems, not control theory, but just dynamical systems. And Vadim is an all-around mathematician. He did his PhD on descriptive set theory, but likes all kinds of other crazy stuff. So you'll hear the word Polish space at some point because of that. So no carry it. A lot of the stuff I'm talking about came even 20 years ago in chapter 11 of my book. If any of you have been to America a lot, chapter 11 means bankruptcy. It was the least downloaded chapter of my book. But a couple of years ago, Ken Goldberg made it required reading for the AI qualifying exam at Berkeley. So I was very happy about that. I'm sure they were not very happy, but sure. So it covers a lot of these kind of things.
What is this place? 2 degrees south of.
I live in Oulu, Finland.
Oh, Oulu, Finland. Oh,
I live at 65 degrees north latitude, and the Arctic Circle is at 67. So let's see. So we have an outside physical world and an internal kind of robot brain. External is state space X. Internal is this information space or internal space I. And again, having the robot's view versus God's view is very important. The robot will rely on things that maybe the designers of the robot may have used some state space model, and the robot relies on that. But it doesn't mean the robot has access to that, because we have to separate ourselves from the difference between a digital twin. The gods kind of know what the world looks like completely, let's say, versus what's inside the robot's brain. So these are quite different things, and they have to be done. When a control theorist thinks of the word state, they usually mean this one, and a computer scientist usually means this one. So it's very interesting, but they use the word state for both, and it leads to at least for me, it led to like 10 to 20 years of confusing discussion. And finally said, oh, no, we're actually talking about internal versus external. Right. So what's going on is there's a coupled dynamical system here. There's a state transition function, a sensor mapping, an information transition function, and a kind of policy showing up sometimes, which we have to design. There's a problem of finding a good policy, which is a planning or control or even reinforcement learning. If you have to call it learning, it's fine. There's a policy for that. Or there's a passive kind of version, which is just calculating updates to the information state, which would be like keeping track of the coordinates as the robot's moving around, as we were talking before. What does a policy mean? So a policy is at every place it tells which way to go. So in this case, the internal and the external are the same. Let's say maybe this is some state space like this, but it could be much smaller in general. And I'll give some examples of that. But the idea is that a robot or some kind of general agent acts by taking whatever its information state is and choosing some action based on that. And there could be disturbances. So this model here has no disturbances. Most people like when they hear the word uncertainty, they think about disturbances, like nature is interfering and causing Gaussian errors and other stuff like that. So we can add that to the model. There's some disturbance coming in to both the way it moves and the way it senses, but I'm not going to do that here, but it's in the paper if you want to look at it. When I use the word information, I mean information in the von Neumann Morgenstern sense, by the way, not in the few years later Claude Shannon sense. So I'm not talking about entropy and all that stuff. It's fine. You can talk about it if you like. It's just kind of orthogonal. It's not really the same thing. This kind of information is more like you don't have the information and you have to make a decision anyway. It's like games with imperfect state information. I've been very inspired by that for many, many years. So we have the history of all things that you've seen so far when the robot's moving around. It has actions it's applied. I gave you an example of that in 1D. And then it has the sensor readings that it got as it moves around. I gave you one, and in my original example, it just has a reading at the end of the string, but it could have a reading going along the whole time. And you can talk about the space of all possible histories. It's very enormous, but that's one way to make a policy. Right? So I want to ask how to simplify it down. And same kind of diagram like I've made, we want to try to break it down to map it down to some smaller space and then live down there completely without ever having to refer back. So I want to throw away these growing histories and just keep incrementally updating all the time with some kind of transition equation. There's a lot of examples of that in the literature, but it's just not been unified together before. The famous Kalman filter is there, which does it over Gaussian spaces, but even time feedback, sensor feedback, all kinds of different cases are like that. Control theorists love state estimation, so others go and try to estimate the state directly, but you don't have to do that either. You can get a lot of stuff done without knowing where you're at, right? Without knowing precisely where you're at. So here's the thing. This is the three people I showed the picture of. This is the main things that they've contributed. Is this framework coming up here, which has really been a lot of nice progress. We love the idea of transition systems. These models, they mainly came from Robin Milner, though they've been around, Turing Award winner, although they've been around in various forms, and they're very closely related to automata theory, of course, and such. But they're just darn convenient for the kind of things you wanted to do. You have a set of states, set of labels, and a transition function, but instead of being represented as a function in the usual way, you take a triple Cartesian product and just take subsets. So you get these triples, and that basically gives you a way to write a directed graph with labeled edges and labeled states with just talking about subsets. And the reason why I like that is because you can do operations on sets and do things in a very, very general way. So one thing that would be very important is the notion of bisimulation. Again, very, very closely related to DFA minimization. But basically, if this is my kind of state machine, this should be the internal information states, or maybe it's external. There's all kinds of different versions that I'll mention. But when you have this kind of thing, the question is, based on, if I'm applying actions and getting observations, is it completely indistinguishable, but no matter what actions I take, and no matter what histories there are, can I get a smaller, or let's say another in general machine that will give the same reaction, so there's no difference of distinguishability. So that's the basic idea of bias simulation relation, and that's very important in our work. What we do is we make a partition of the state space using another labeling function. So the edges are already labeled, and then we have another labeling function which labels the states. And the only reason why we do that is because we want to get a nice partition of the state space. So any function you make that goes from states to labels has pre-images, let's say, right? It's a many to one mapping, let's say. In general, we want to assume, instead of now make a 5-tuple, that's just a transition system with some extra pieces. And then one general result that we showed was that for any deterministic, and by deterministic, it means that for every possible state in action, there's some next state that comes out. You can't just have, I applied an action and I die, which is fine in NFAs and stuff like that. Or I applied an action and I don't know, I went to these 5 states. So the deterministic means it's not that. Every state relabeled, so no matter what you pick for these guys, there exists a unique and minimal linear, not linear, labeled transition system that is by simulation equivalent to it. So unique and minimal, which I found quite shocking. Minimal, maybe unique. Wow, that was pretty cool. So that also corresponds to the course's kind of refinement of partitions over the state space that you can get that are sufficient. So we end up showing that there's a complete lattice inside of there of partitions. Everything's really nice, and the state space and the lambda can be any sets, and I mean any sets in like a ZF set theory. So like this is where Vadim tells me it can be anything. It can be function spaces of Polish spaces and all of that kind of stuff. It doesn't really matter. So I mean, ridiculously general, as long as it fits into Zermelo-Frankel set theory. So whatever you like. So I think that's quite remarkable, and it's the same kind of result. And this deterministic thing is just like what you get for DFAs. If you do DFA minimization, you get a unique minimal machine, and if it's non-deterministic, you don't get uniqueness. So very similar kind of thing. So this is great. It applies to anything. So I can just apply it right here to our example. I put my various pieces in there. The labels are actions, and I have a sensor mapping there. And then what should pop out is that you get this, if you had a method for solving it, then what should pop out is you get this minimally sufficient information space, which corresponds to Z. Or you could have already known that that you have an external state space representation already. This is without even having an X defined. Or you can define X, and then it'll just say, well, you already have it. So it'll actually come back and tell you that you found it. So you can either find the right representation somehow. I use representation with kind of lowercase r, like not in like an inactivist sense, like a meaningless representation, let's say. Or you can be given one and you can refine it or improve it in some way, or be told that no, that's the right one. So it could be the case that the internal and the external are different. So for example, maybe my sensor just measures the position here mod 5. So I get, it's equivalent to putting goals every 5th point here. And then I can put this together. I get the information space for this is just Z5, and it just keeps going around cyclically. So that ends up being the minimally sufficient information space for that problem. So generally speaking, this minimal internal I is much smaller than the external X. It should be for the kind of problems we care about. There's a lot more examples of that. I'm going to blow through some kind of fast. I've kind of given the main kind of ideas, but I want to go through some other things. Here's one where you just want to make a filter. We did this maybe 20 years ago with some students like Ben Hamid Tovar, some others. Fred Cohen's a mathematician, passed away a couple of years ago, unfortunately. But we have anything you want to track. Could be a robot or a human. It's moving around, and there's these sensor beams, and it generates a string based on which one of these beams gets crossed. And they always get crossed transversally. There's some general position assumptions. And so if I have a pair of things to track, and I'm looking at the strings of them, I just want to keep track of whether or not these two guys are in the same room. There's 3 different rooms here. And we found, after a lot of thinking, that this is the best way. This is the smallest filter you can make that keeps track of that information. Either they're together or they're not. If they're not, they're in one of these 3 information states. And each one of these corresponds to, they're in different rooms, but with C as the boundary between them. And so this thing just transitions very naturally. It's a very small information space. Let's give you an example of, I don't have to even keep track of their exact positions. I don't even have to keep track of which room they're in exactly. I just need this little, 2 flip-flops to keep track of this. Going back to this, you can even have minimal policies. So what if I don't care about, I hope I mentioned it, but maybe I didn't, that we're trying to predict when the sensor is going to fire to learn the environment. So what if I don't care about that? What if I don't care about that? I want to be even more minimal. All I want is a strategy that's just guaranteed to get to the goal. So imagine you're moving on it's like a circular track, because this is the same as this. It's just identification. So this thing's moving along, and I just want to be guaranteed to get to the goal. So it turns out a constant action is fine, right? Just keep moving forward, and it'll work fine. So we also studied the problem of trying to reduce the strategy that you have as much as possible, even if you don't care about surprises. So the first one was eliminating surprises altogether, this minimal sufficient information states for filters. But we've gone even further to try to say, okay, what are the minimal policies? that the simplest policies you can make, that even if they're surprised, when they might be surprised when they get to the goal, but they always do it, put it that way. So there's many different versions of this, like based on, do you put information histories in there? You can put actions and sensor observations. You can do it from any information space. You can put the external state space in there and sensor mappings. You can also put a policy in there and try to optimize that. As I said, there's a lot of different ideas here. It's related to some ideas going back to Mike Erdman from CMU and Michelle and O'Kane and others. So, but anyway, we've used the same kind of general framework over and over for different kinds of problems and cases. So let me give some more kind of examples and things to get you thinking. So here's a basic mapping problem. So again, 1D again, the robot's moving back and forth, and can it learn to distinguish between these two? So if it's going back and forth here, and it keeps hitting on a track, or it goes on forever, what does it take to distinguish between these two? This looks very much like what's called the loop closure problem in robotics. It's not a robotics picture, but I usually like to use this picture in continuous cases. Is the robot on a circular track or a helical track, but it can't measure the height, right? So there's a very basic notion of confusion. We started studying these kind of problems systematically recently. If you had maximal distinguishability, you end up with something like this, a kind of binary tree that goes on forever. This is going back to my original 1D example, starting on Z. So I have forward, backwards, forward, backwards, forward, backwards, and every one of these nodes ends up being the same. And then through sensing, we can discover, oh no, this is the same place, or at least as far as you can tell with regard to sensing, it's not really thinking like that because it doesn't have beliefs and such. But we can start identifying some vertices in this. This looks like the Cayley graph of a free monoid. And if we go a little further, we can allow some ambiguities here and such and start getting all kinds of different confusability. Let me give a more interesting example. Suppose you have a robot now with kind of looks like 2 tracks here, and it can move off in one and come back. But when it comes back, let's suppose it's not sure whether or not it's in the same room it took off from. Like it's lost in a cave. Comes back, yeah, look, is it the same? I'm not sure. You know, you don't have good odometry, and you're trying to figure this out. So this is kind of a very simple way to represent how it looks. So there's a 4-way junction there. And what are the different possibilities of confusion? Well, if you're going to be really conservative, you say, well, I'm going to be safe. I'm going to always assume it's not the same place. Then you end up with a another kind of Cayley graph of a free group there. It looks very nice. And then you end up with pictures like this for lots of other cases. Now, I did not get these pictures from a robotics book. I got these pictures from an algebraic topology book from Alan Hatcher. And I was reading this book online. And actually, my planning algorithms book is free online. And I told him I wanted the Alan Hatcher deal because he did it a couple of years before me with his free online book. And anytime I saw this picture about covering spaces, I thought, oh my God, this just looks exactly like confused robots, right? So I was talking with Vadim Weinstein, my collaborator in the group, for years about this, and we eventually, mainly him, put together some really nice theory to explain these things. Oh, now it's back to the frozen part. Oh, no, it works. Sorry, it's just a delay. You'll get some exercise there. Yeah, so the basic idea is we have a very general model, and I mean general like Polish spaces, kind of general model for sensing actuation environments. It has both a differential kind of version, like manifold-based one, and a topological one on Polish spaces. I guess people can't say like Sierpiński, Kuratowski, and Karski, so they have to say Polish.
Okay.
Some can't, but I don't know. Only the Polish can pick on with that. I don't know. So let's see. So the general result that we have is that if two different environments, there's a very formal definition of an environment. I'm just giving you the flavor of it. If two of them, if there exists a covering space or a cover for 2 environments, then they are bisimulation equivalent. So they're equivalent in some very nice sense, which basically means that we have a notion of historically equivalent. Like all the histories you'll ever generate of actions and observations that you get from sensors are going to be identical. However, the lack of a cover does not imply bisimulation equivalence. They can be equivalent without actually having a cover, which is interesting. And Vadim likes to say this, it's actually, and pay attention, everyone, this is an application of robotics to mathematics, not the other direction. So he says, it actually, the paper produces a method to prove that 2 spaces do not have a common covering space. So by making this kind of simulated robot that demonstrates that it's not possible. So this is a one-way result. So you can say not covering implies, you can say not equivalent implies does not exist a common covering. So I thought that was cool. And there's many open questions in that paper. It's published in this book with Farber and Gonzalez. Farber is the famous topological complexity mathematician.
I was here. He
And
was
he-
in the math department.
I'm not surprised. Yeah, that's cool. That's right. So this is like the second installment of that math book. So we have a paper in that, like. The work we did a long time ago, we were able to, in the current framework, show that it's in fact producing the minimal information space, which I thought was cool. So Bashak worked really hard on that one. And so the idea is we have something called a gap sensor, and this is not a real sensor you buy, but it's basically just measuring discontinuity in depth. And that's all it senses. So there's these gaps or discontinuities in depth, and they're combinatorially ordered around the circle. You don't have any other metric, no metric information. Not other, but no metric information, no angles, no distance. But yet, you can get it to do distance optimal navigation. So you can move by just chasing gaps. So the robot sees a gap and it goes for it like this. And then the gaps correspond beautifully to some kind of generalized bitangents, whether it works for piecewise analytic environments or curved or polygons and stuff. These aren't fed into the computer necessarily. They're just the assumption of the environment. So if it goes back and forth across this, then a gap appears or disappears. If it goes across some kind of generalized bitangent, gaps split or merge, and you get these nice kind of tree structures, which I think, let me see if I can. Maybe this might play. Yeah, this is just, oh wow, that's cool. It shows up here, but not there. So I don't know how to, well, I'm worried. Anyway, there's a cute animation that shows how that tree was made, but there's a general kind of tree that's grown from these splits and merges, and that the space of all trees ends up being the minimal information space for that problem. And it lets you do distance optimal navigation without being able to measure distances. So that's, I'll say it again. You can do distance optimal navigation without measuring distance. And the computational geometers usually say, yeah, we know that stuff, that structure. And that's kind of true, but, which is amazing, but this is being found from a robot that doesn't have a polygon as input or something. It doesn't have the ability to localize itself. So it's all done just from mathematical models of how the thing navigates in an unknown environment. And it's able to learn the environment well enough. It's a simply connected environment, and it's able to learn that well enough. I think maybe it works. Oh gosh. I don't. Yeah. Oh, that's a different video. Wow, that's interesting. Well, it's not going to work too well. Oh, because it says preview. Oh no, it's gone. Oh, there's the first one. It's probably like, okay, 0.5 frames per second. I don't know, but anyway, so it moves around and gradually, but that's that tree is its representation of the environment. And it's just minimally enough to do distance optimal navigation. Thanks, that's cool. So let's see. Oh. Now I'm frozen on that. I probably shouldn't exit too much, huh? I do have one more thing that, okay, well, let's see what the other one's not an animation. Robot illusions. We have a ERC advanced grant on perceptual illusions and perception engineering. I just want to very briefly mention, you can add a third space, which is here, omega, which is like the universe. It's like the ultimate truth. And then there's X, which is what the engineers, who are like smaller gods, but not the gods that run the universe, design the robot with. And then there's the internal workings of the robot. And we ended up with a pretty nice theory, which it has 2 or 3 simple relations, a model relation. I'm going to run out of time, but basically you end up with this associating information states with states of the universe, and it basically ends up being an illusion if it's plausible and does not correspond to reality. I don't have time to go into the details of that, but it basically is a couple of simple steps. But it's very neat. So first we had just X by itself, and I say, no, these are different. There's X and I, but then when you bring in omega, you can actually do virtual reality for robots. And here's some simple example here. It goes back to our confusions that we had before. You can confuse a robot into thinking it's on a circle or a treadmill or something, if you like, and it's really going out forever in both directions, or the other way around. We also did some work in fooling a little vacuum cleaning robot, where this researcher Markus Suomalainen was a virtual reality display, which meant that he presented obstacles to the robot every time it tried to vacuum in a certain direction, and it said, okay, the map's this small, and I'm done vacuuming. So we can fool robots by doing these kind of things. So we have a whole theory of illusions. I want to make sure I have time for this extreme minimalism thread. So I want to get kind of ridiculously small. How dumb can the robot be and still do things. There's also this idea Mark Graber likes to say of mechanical intelligence. I never know what intelligence means, but basically mechanisms can do surprising things. I'm afraid to show this robot moving around. But how much work is it to get a video? Is it?
Oh,
Do I have to go back? Is it just so just try it, or should just click and run maybe? Okay. Oh, there we go. Yeah, it's not going to work too well over this thing, but this is an exploration robot. It can escape any. It's an escape robot. Let's say it can escape any room. It even goes down into this little pocket here. Like even tries to. If it runs long enough, it'll try to escape through it. But there it goes. So that's a really clever exploring robot. But basically, it's just something called a weasel ball. There's just a weight inside of here, and it just oscillates at about 2 hertz, going, and there's no computation at all. That's enough. I don't need to go back to. Oh, well, I can't say. I want to go back out in a minute. There's some more like this. So we started. There's some work on. I don't know if you've heard of dynamical system billiard problem for mathematical billiards or dynamical billiards, where you just like hit a ball and it bounces all around. So these are really fascinating. You get ergodic trajectories for almost all polygons. So there's very interesting results like that. And we did a bunch of work with a whole bunch of these balls moving around, and we can control them however we want. Let me see if I can. This ergodic trajectory thing. This goes back. There's a lot of studies of that coming from Russia. The students of Kolmogorov, like Sinai and Bunimovich, who was his student, ended up doing all these like Hamiltonian system things that were nice from this. Some little Python I wrote, but you can see it kind of just bouncing around in a. This is what a computational geometer calls a simple polygon. A control theorist calls a simple polygon like a square. Anyway, it's ergodic, so it goes all kinds of crazy stuff. So you can get a lot of power out of that. And then, well, we did information feedback, and we can control robots doing this kind of bouncing principle. I'm going to run out of time. I want to make sure I cover at least a little bit of this universal plan stuff. So another one of the mathematicians I mentioned, Kalle Kimperi, he introduced me to this paper by Rudolf Kalman, the same Kalman filter guy. He wrote kind of later in life called Randomness Reexamined. It's a fascinating paper. It has a lot of like grumpy old man kind of syndrome to it. So it's very nicely done. And I thought it was really cool. But basically, he was really upset with the way people were claiming probabilistic revolutions and being all Bayesian and all this kind of stuff. And he's the Kalman filter guy. He thinks everyone totally misunderstood his method and abuse it all the time. So, and he said it's a big difference between randomness and probability. Very important to understand that. So so anyway, that inspired this work a bit. My reading of that, and then Holly and I worked on this. Worked with my son Alex too on it. So basically, you have a robot moving on a grid, and it can be presented with any possible environment from an infinite collection of environments. Every environment is just a set of white tiles, and it moves around with the usual 4 movements. However, if you ask the robot to move and there's an obstacle in the way, then it just doesn't move. It can either do that mechanically, or it can do it with some very simple dumb sensing, but it's memoryless robot. So the robot never has a model of what's going on inside. And I want to ask the question, does there exist a single plan? And a plan is a sequence of actions. Does there exist a single plan that solves every single problem? Doesn't matter what problem you feed it, it'll just solve it. So the robot will always get to a goal. Problem means it has to get to the goal after a finite number of steps. And it can have a goal detector and say, okay, I've arrived. It'll be a surprise when it gets there, but that's the idea. So we use normal numbers, which I'll get lost if I go too much into the details of it. But basically, Borel showed that almost all real numbers are normal, which means that every sequence of length k appears infinitely often and with equal frequency. There's something weaker called rich numbers, which is also all we really minimally need. But people believe pi is a normal number, but they still can't prove it after all the time it's been conjectured since Borel. They've constructed some like Champernowne or the Copeland-Erdős. One is these are just prime numbers, just kind of written out as digits. So this one, Champernowne, is really easy, just 1, 2, 3, 4, 5, 6, just counting. Right, so these are proved to be normal numbers. These are much better behaved in some sense, but nobody can prove that they're normal numbers, except Borel, who proved that if you pick a real number at random, it's normal. But nobody can show that any particular household variety, pi, square root 2, golden ratio, nobody can prove that any of those are normal. Anyway, so that's kind of weird. But what I would say is just go to base 4 and feed those digits into the robot. So if you do that, then you know the problem's not written on any tape or anything. It's memoryless robot if the gods provide the action sequence. Otherwise, you need log n space. There's an interesting unpublished paper by Chi Yap that shows that you need only log n space to produce the digits of pi. But Champernowne's digits you can produce for sure in log n space as well with much simpler arguments. And however, it's the n here is the number of steps, not the number of white spaces. So how those are related is much more complicated. And then what we proved, building on a work of Compton, so it's very closely related to like what do you call it, like zeroing out automaton and things like this, automaton reset problems and things like this. That basically these normal sequences and rich sequence more weakly solve all grid problems and deterministically, not probably will, but they will. In a finite number of steps, solve every single one of them that's presented to the robot. And even works for more general directed graphs. We have an n-dimensional continuous version as well. I'll see if I can show that playing out in a minute, and then just kind of finishing up. And then if the robot's able to detect when it reached the initial end goal and record the actions along the way, then it'll actually converge to optimal plans. But the caveats are, it'll never know when the optimal plan has been reached already. It'll just see the sequences getting better and better. So you can never declare, okay, this is the best possible. And it cannot just, it's not a decider, so it can't decide whether or not there is a goal. But that's a lot like our sampling-based motion planning problems. This is kind of how it looks, exploring using pi, using Champernowne. This is exploring mazes, but this is like just a superposition. It's on a time trajectory. I want to play this one just to show what it looks like a bit. This is the one that's doing. Oh, to do it in continuous spaces, it also uses the digits to change the step size. So this is just running over and over again using digits of pi, starting from a different place in the digits of pi, base 4. And it has to hit this goal from that initial up there red. So they're not too bad. They don't look that ridiculous most of the time. Sometimes they get a little bad. So again, the robot doesn't in advance know any of this stuff. It's just applying this kind of blindly. So it's the most idiot robot you can think of, except for the weasel ball, which is even dumber. But doing this. Let me try to wrap up here.
Is this practically useful?
Well, we built a real robot and it does what it says. I think, well, it's at least as useful as a random walk. And those have been used all over the place. So, but this one has deterministic guarantees. So it's more, I get tired of all this asymptotic this and probably that. And I'm like, no, it works. Deterministic, it's guaranteed. So weird. So I like the theoretical properties more than the practical difference, but I think in a lot of cases where people run to use randomize this and that, you may be fine just doing this deterministic stuff. There's nothing wrong with it. These are like God-given digits, they're from pi or well, we can't prove those are normal, but the other ones we can, and so it depends on whether you want to prove or not. But, some sensor lattice stuff, I'm just going to skip this. It's sad though, because this is the stuff that some of it was done in collaboration with Danny and his students who are here. So Michael Vilovich and Barak Ugal. And I'm just going to show some of the results here. Sorry, you're going to get kind of squeezed out. Very neat. But basically, there's a theory. This is all a special case of the things I've been talking about. It corresponds to intersections of preimages and triangulation of sensors and such. But very generally, we have these partition lattices that I was talking about. They occur for any transition system, and they occur for the things I skipped, which are special cases in some way. And then you try to figure out the right resolution to engage with the environment with. I showed this slide before. I'm just saying it again. There's all these different ways to use this very general theory, which again applies to function spaces over Polish spaces, or more Polish spaces, and I don't know, whatever, Ukrainian spaces too. It doesn't matter. This is how it feels to me after about 30 years of working on this. It's like the pieces are all falling into place. We kind of have the frame. There's still a lot more to go, but this is helping like clarify a lot of things that I intuitively felt 20 or 30 years ago. But the pieces are fitting together with clear mathematical description, which is really nice and very high level of generality. This is the last slide, I promise. So what are the general messages? Don't sense everything to make a digital twin and then do a whole bunch of computation to figure out what you needed, or just throw piles of data at necessarily. It's helpful in some context, but sense what's needed and forget the rest. So maybe you need architectures that properly forget what you don't need. That's what's going on in a lot of these cases. This transition system model provides some kind of guidance, and we're in the process of formalizing a lot of our other works that we've done, as well as other people's works. Predictive state representations and POM-DPs, a lot of other things that show up in AI, we can encode in these kind of ways and study them, so they fit into the framework as well. What about deep learning? I think the end-to-end learning part is great because they expose the burdens of the obstructions of modularity. You know, do we plan a path first and then generate a trajectory based on the path and then generate a feedback control based on that? Oh, and build a map before we did all of that, build the environment. No, we could just do end to end. That was always true. We just didn't want to do it. It's a lot harder to do it. So a lot of other methodologies by getting rid of them. How will neural nets ever find these minimally sufficient structures that I talked about? You're not going to get that. You're just going to get the parameters of your neural net. So I don't know how it finds these structures automatically. These things I was talking about, right? Like that 4-state minimal information state transition system for a filter. How does it find it? And hopefully there'll come along some robotics based neural nets that have different kinds of symmetries, like the relations I showed you that are more appropriate for robotics. The relations for computer vision were translational symmetry, which CNNs use, or permutation symmetry, which LLMs use, and these kind of things. So what are the right kind of relations that are worth an infinite amount of data? And there's algorithmic challenges all over the place. I didn't really throw the big O around very much here, if at all. And so there's a lot of the stuff is more still in the like decidability kinds of questions and such. But there's a lot of room for algorithmic. You know, when do we think to find these minimal structures, or when can by hand, or when can we do it automatically? And again, I'm always bumping up against results in computational geometry, and there's a good reason for that because I think there's a quest for minimalism there because of the interest in complexity. But they're coming up in kind of a different way. So thank you very much.
How would you model a robot that changes its environment? Say, Roombas tend to do that.
It changes its environment by vacuuming?
By pushing around stuff, making new pathways.
Yeah, so you can make the well, let's just take dirt, right? So it cleans up dirt. Like the oldest Roombas would do like wall following along the dirt boundary, and they would just spiral in and get the dirt that way, because you're changing the environment as you go. So in order to do these proofs and things, with the godlike model, we have to make a representation of that somehow. So we have parameterizations or descriptions of what's possible for the environment, what kind of transitions are possible. So it's fine. It makes a much higher dimensional state space, but it all fits inside of a Polish space, so it's fine. I mean, at the general level. Yes.
Do you think that something like with the work that you did with your kid, your child,
Yeah.
and used to prove something like P equals VPP, and like more like much more in a more complicated way?
All these universal plans?
Yeah.
I don't know. Let's talk about it. I mean, it's kind of weird to me. It's I don't know. There seems to be something really fundamental. I mean, one thing I've been bothered by for a long time, I didn't have time to talk about this, but there was a great belief that random sampling is helping you in motion planning. And we showed that deterministic sampling is at least as good, and in lower dimensions, it's probably better. And so there's this belief that randomness comes to the rescue and helps you. And okay, it's kind of helping here, but it's a different kind of randomness. It's the kind that Kalman said randomness re-examine randomness. It's the kind of randomness like the digits of pi, but not the randomness that we have to do it probabilistically.
But all the randomness, all the practical randomness is pseudo-random. It's like the digit by itself.
It's correct that if a computer is using so-called random numbers in a so-called randomized algorithm, it's ultimately using a pseudo-random number source, which is based on Mersenne primes and Mersenne twisters and other kind of basic number theoretic constructions, right? That's exactly right. So in practice, they're doing that anyway. But what happens is those sequences are trying to simulate or approach certain distributions that probabilistically, right? So they should pass certain statistical tests. So in these cases of like, for example, you may be wanting to explore a space for motion planning, and the sampling is going to happen with replacement. Like maybe it's going to be, and in order to sample some two-dimensional space kind of randomly, it needs to have too many points in some places and not enough in others. If it's too uniform, it doesn't look probabilistically random anymore. It doesn't look like it was sampled according to a uniform distribution. So sometimes these deterministic sequences, by making that your target, can be more uniform than uniform random. because they're targeting a different distribution.
Can you say a few words on the finding minimally sufficient structures with learning method?
Yeah, I guess we can go all the way back to like just like linear regression. You know, linear regression. I want to fit a line to some data. I have a couple of parameters, right? The slope and intercept of the line. All I can do is find those parameters. We know high order polynomials work. They shoot off to infinity here and there. So we have neural nets, which with a whole bunch of parameters and a whole bunch of data can learn something that's, you know, a lot like fitting a line in some way. But all you have are those billion parameters, let's say, whatever they were for that. But they're not. I don't know how to write it in such a way so that it's telling you it's finding exactly this minimal structure. All it's doing is tuning. It's finding some good values inside of a predetermined structure. So it's an open learning kind of challenge. Like, for example, for that 1D problem I said, so imagine a robot stepping around. I wouldn't mind considering the robot to take 1,000 steps. That's not very much for a robot. Even 1,000,000 steps is not very much. So am I going to feed all strings of length 1,000,000 into that's 2 to the million, you know, as input data to figure out how to predict what the sensor is going to do? Or maybe I only feed in only 2 to the 1,000, all digits of length 1,000, and then I want to predict what the sensor is going to do at step 10,000. Is it going to be a good predictor for that? Probably not. So these are weird kind of things. We're starting to think about this a bit. That's how it looks to me.
Lateral regression or information bottleneck, or like which approach do you have in mind?
No, I think I'm in a mode where I'm more like these lower bound, you know, complexity theory, computer science types, where they're saying, look, it's scary. This is really hard. And like you need to have at least this much to learn this or something. But I don't know. Coming the other direction and trying to solve something. I want to say that there's some really hard problems here that maybe this style of learning might not solve. All these things are learning problems in some sense, but who's doing this? Is it the human doing some of the learning by thinking about it and trying to find these minimal structures? To do it autonomously with an algorithm,